Welcome back. Let's continue with more theorems on field theory. So in this video I will be discussing second isomorphism theorem, that's lemma G7. Before moving on to this theorem is actually proved with the result of first isomorphism theorem. So I have done first isomorphism theorem in part 2 video of field theory. So if you haven't watched that video, please do watch that before seeing that. I will be given the link will be given in the description box. Okay, let's move on to the statement. We are given two subgroups of G, that is K and H, with K is normal in G. So we are supposed to prove two things in this theorem. First is we need to prove K intersection H is normal subgroup of H, and the next one is the factor group H by K intersection H is isomorphic to KH by K. So we are supposed to prove these two things out there in this theorem. Okay, let's move on to proof. So for proving K intersection H a normal subgroup of G, I am defining a function pi from G to factor group G by K. So it's a natural map which is defined by pi of x is equal to xk. Natural map in the sense, if you take an element x from G, the corresponding mapping will be to G by K. So that's what meant by a natural map in the sense. Okay. So we are supposed to prove pi a well-defined function. For that, take two elements in G with x is equal to y. So two elements we are taking from G with the two elements are x and y with x is equal to y. So from the property of coset, it is clear that xk is equal to yk. So how done in the same way we took cosets in the previous video, here also we are taking the same way coset, that is xk is equal to yk. So now define pi of x is equal to, y of x is defined in the way like y of x is equal to xk. So we are taking the definition. Now pi of x is equal to xk, which is nothing but is equal to yk, which is equal to pi of y from the definition of pi. Okay. So it is clear that pi is a well-defined mapping. Now we move on to the second part, that is we need to prove pi a homomorphism. For that, again we took two elements x and y from G, and pi of xy from the definition of pi, it is clear that pi of xy is equal to xy into k. Pi of x is equal to x into k. So similarly pi of xy is equal to xy into k, which can be written by the property of coset as xy into k, which is equal to x into k into y into k. So x into k is nothing but, from the definition of pi, it is clear that x into k is pi of x and y into k is pi of y. So it's clear like pi is a homomorphism. So the first part is over. Next we are supposed to prove isomorphism. For that, let's define a mapping. Let's define a restriction, that is f from h to g by k be a restriction pi restricted to h, that is pi is restricted to the domain of the function, that is h, pi restricted to h. So f be the corresponding restriction of pi restricted to h. So let's take f of x is equal to xk for all x belongs to h. So we have proved in the first part like phi is a well-defined function and phi is a homomorphism too. So we have proved those things in the first part. We are taking that from there. So since pi is a well-defined and homomorphism, f is also well-defined and homomorphism. So f is actually defined from h to h by k. So if pi is a homomorphism and a well-defined function, so similarly f is also a well-defined and homomorphism, that is homomorphic function. Okay, now define kernel of f as we define in the first homomorphism theorem, first isomorphism theorem. The same manner we are proving here too. So we are defining kernel of f. So it's clear from the definition itself, which is equal to set of all x belongs to H with f of x is equal to k. So f of x is nothing but xk. So we can replace f of x by xk, which is equal to set of all x belongs to H with the xk is equal to k. F of x is nothing but xk. So xk is equal to k, which is equal to set of all x belongs to H with the x belongs to k. So xk is equal to k. So that one belongs to k. That is kernel of f is equal to k intersection H. Set of all x belongs to H with x belongs of f is nothing but k intersection H. Now we define image of f, which is equal to set of all xk which belongs to factor group g by k, where x belongs to H. So we need to prove that H by k intersection H is isomorphic to kh by k. For that we took the element kh by k, which is defined as set of all xk with x belongs to kh. We know that h and k are subgroups of G. So by lemma G6, that is given in the video 2, a second part of field theory. Okay, from that we can write like hk is simply equal to kh. So instead of this we can write it like set of all xk with x belongs to, instead of kh is equal to hk. So x belongs to hk by lemma G6. Okay, so which is equal to set of all xk with the, I am taking my x to be an element small hk which belongs to capital HK, which is nothing but if I group these, okay, which is equal to set of all hk into k with h belongs to h and k belongs to k. Now I am taking hk into kk where k belongs to k. So hk into kk is nothing but k. So hk into k, which is equal to set of all hk into, instead of k I am writing 1 into k, that is nothing, 1 into k with h belongs to h. Now I am grouping these elements. I am taking 1 and h together and k is keeping apart. So which is equal to h into 1 by the property of cos x. Okay, h into 1 into k. H into 1 is nothing but h into k, that is hk with the h belongs to capital H. This is nothing but the definition of image of f, which is equal to image of f. So we have our function f defined from h to g by k, factor group g by k, which is a homomorphism we have defined. So we have got like f is a homomorphism. Now we have seen first isomorphism theorem, right? So what was given in first isomorphism theorem? We are given a function f from g to h, which is a homomorphism, and kernel of f is normal subgroup of g, and g by kernel of f is isomorphic to image of f. So from first isomorphism theorem we have kernel of f is equal to k intersection h. So which is a normal subgroup of H. And so from first isomorphism theorem we have g by kernel of f is isomorphic to image of f. So here instead of g by kernel of f we have h by the factor group h by k intersection h, which is isomorphic to image of f. Image of f is nothing but kh by k, which is equal to kh by k. So that's what the theorem is. So we have proved, yes, we have given two subgroups and one is normal in k, then k intersection h is normal subgroup of h, and we have proved h by k intersection h is isomorphic to kh by k. So second part is actually proved from first isomorphism theorem. So if you haven't watched that video, please do watch. So thank you.